Alright, this should be the values that you get here. I believe. Are you guys getting the same thing, or is there one that's different? You are right. It should be negative. And that explains why I was getting something weird when I did this. Let me see. Okay. Now, notice that we have some residuals that are negative, some that are positive. If we have a negative residual, that tells us that our dot is a little below the line. If we have a positive, it tells us we're above. So if you, for example, if you had a residual of 3.187, that would mean you did 3.187 better than you were expected to do based on your GPA. Whereas if you had, so like for example right here, if we looked at maybe, let's see, these two right here were very close to making the same grade. This person made a 22, this person made a 23. They're very close to each other. This one is 1 point better than the other one. But you could argue that this student did significantly better than you would expect this student to do because they have a 3.9 GPA. So you would expect them to do higher. They did a little bit less than you would expect them to do. This student only had a 3.2 GPA, yet got a 23. They did they're 3 points above what you would expect them to do. So not only was their grade just a little bit higher, but they also performed much better than expected. Now, GPA doesn't tell you everything about how well you're going to test ACT, so it's not perfect. But do me a favor here. Take all of these numbers right here, all of your residuals, I want you to add them up for me. Add all of those together. Either one's fine, yeah. Whichever you prefer. Okay. What'd you guys get?
I got 0. I got 0. Wait, I don't know what I did.
Are your numbers the same as mine?
Wait, are you adding them all?
0's even better than what I've got.
Are you adding them all?
Okay. It should be negative, right?
But you subtracted it.
Plus negative, same as minus. That is not the reason this is wrong.
I got 0. I'm 0.008.
You got a different number on one of these?
I just want to go home.
All right. Let's see if I typed them in right. Negative 0.009. Is that what you guys got for the first one? 3.187 for the next one. Negative 2.204. Negative 3.197. Positive 0.663. You guys get something different there. What'd you get? 623. 0.623. I thought it was supposed to be 0. And then we've got the others. And now I'm getting 0. I thought it was supposed to be 0, but that it just had turned out to be 0.04 because of rounding, because that could happen. But if you have a line of best fit that fits the best as it possibly can statistically, it's a linear regression, a least squares regression, these residuals should add up to 0. Because if they add up to 0, that tells you that the amount of distance that you're above the line for some of them is equal to the amount of distance you're below the line for others. So if you do it correctly and it is a line of best fit, then you should get 0. If your line does not fit well, then you may not get 0 for that. You may get a different number if you add those. Excuse me, all together. All right. So something that you are going to see on these problems are called residual plots. Okay, residual plots. So here we are supposed to make a residual plot for the GPA data. So I really need. I need the table that I have on the last page is what I really need. I can do this. Let's do this. Let's add another one right here. I'm going to enter those residuals. So, -0.009. -0.009, 3.187, -2.24, -3.197, 0.623, 3.007, -1.407. Okay. All right. Okay. I want everybody to make a residual plot along with me here. So you have the table that you have on the last one you can look at. I can't flip back and look, so I put it over here in Desmos. So you don't. I just put it there because I can't flip back and look. So what is we know a GPA of 0 would be right here. I'm just going to put 1, 2, 3, 4. Actually, no, let's go up to 5 because some of these GPAs go above 5. So let's go 1, 2, 3, 4, 5. So what we're going to do for this is we are going to graph our x-coordinate along with our residual. Okay, so we're not graphing the y-coordinate, we're graphing the x-coordinate and the residual. What is our highest residual that we have? I think we have 3.187, but close, around 3, right? And then we have around a -3. So on my y-axis, I want to label this 1, 2, 3, 4. And I also want to have -1, -2, -3, -4. It's very important to label that axis or whatever you're graphing really doesn't matter. All right, so what we're going to do is we're going to graph these points. So we got 4.2, -0.009. So 4.2 is about right here. -0.009 is just barely going to be below the x-axis. Then I have 4.5, 3.187. So 3.187 is going to fall about here, a little above 3. I've got 3.9 and -2.204. And then I've got, let's see, did I just do 3.9? Yeah. 3.4 and -3.197, so maybe about right here. 2.1 and a 14 is just a little bit positive right there. 3.2 and 3.007, so right here. And 4.1 and -1.407, so about here. You can actually see where I added these in right here. Where I added these in as a Y2, it actually graphed it for me over here. Let me make this go away. So it graphed it for me right here. Get rid of this. So you can see these points look pretty similar to what I've graphed over here, right? This is a residual plot. It shows us how far off our numbers are on the graph. Okay? So what would this residual plot look like if my data was really, really, really good? What if it was perfect? What if it fit the line perfectly? This is what, so I'm talking about, not about the original, but like I'm saying all these green dots from my line of best fit, what if they were perfectly on the line?
It would just be a straight line.
What kind of straight line?
Horizontal.
Okay, horizontal?
Yep.
At where?
At 0.
At 0, because all your residuals would be 0 if your line was perfect, right? So the closer these dots are to that line, the better your data is. The further away they are, then the worse the data is. So these can be used to kind of see how well your line fits your data. Okay? So let's talk real quick. We've already talked about this some. Correlation. We definitely have talked about correlation coefficient. What in the world was correlation coefficient? So our R is correlation coefficient. R squared is that number squared. Some of the ones we looked at, you could only see the square, like the exponential and the quadratic. So just the plain R is technically that correlation coefficient, but both of them will give you information you need to know. So correlation just describes the relationship between two variables. It can be strong to weak, and it can also be positive or negative, right? If it is positive, then that means your data is increasing. If it's negative, your data is decreasing. If it's strong, they look really a lot like a line, and if it's weak, then that looks not much like a line. All right, so we can have two variables that are correlated. What's important, though, is correlation is not the same as causation. Okay? Causation implies that one variable causes the other variable to change. Okay? Correlation does not always imply causation. Okay, so let's talk about some situations where that would be the case. Okay, what do you think?
Cheese consumption with global warming, right?
Those are
They would both go up because of population.
correct. That's a good example. So cheese consumption and global warming, if you graph them, if you have cheese consumption on the bottom and you have global warming on the y-axis, you're probably going to see as cheese consumption goes up, then global warming also increases, right? But do you think that you eating cheese is the primary cause of all global warming?
No.
Yes, obviously.
Wait, it might be.
If we just quit eating cheese, everything would go back down.
The government's telling us lies, I'm telling you.
Okay? Cheese only. So while I do realize that farm animals do produce like methane gases and stuff that add to this,
Most of it's food manufacturing.
your cheese consumption may in a very small way affect global warming. But as Evan said, the real thing behind it is that if we're eating more cheese, it's probably because there's more people, right? And then if there's more people, those people are also doing all kinds of other things. So we could not say that cheese consumption is what's causing global warming, but we could say that they're correlated, that they have a similar trend, right? So that's a very good example of that. Can anybody think of a different example where you might have two variables that are correlated, but they don't necessarily cause each other? One thing that you have to be really careful of, you got another one?
Never mind.
Okay. One other thing you have to be very careful of is often you will look at like two variables that may describe performance for like different groups. but it doesn't necessarily cause that to happen. For example, you may look at socioeconomic status, so how much money your parents make, versus college acceptance rates. You're probably going to see the more money your parents make, the more likely you are to be accepted into college. I'm not saying there's not some causation there, but it may not necessarily be all caused by the same things, right? You might, so like for example, people who have higher paying jobs probably are educated themselves, right? So they may, so it may not just be the money, it may be other things as well. So you have to be careful on like boiling things down to just one cause, right? There are many different things that might make us successful in school. Money could be a part of it, because if you have sufficient money and you don't have to worry about where your next meal is coming, that takes away some stress and allows you to focus. Or you might have resources for tutoring and for different things. But money may not be the only factor that causes that to happen. So in general, if you see, I don't know if you'll see any questions on the exam or not about causation, but you pretty much can never make the assumption that because two variables are correlated that they definitely one causes the other. It might provide evidence that one may cause the other. For example, if we give somebody a drug, like a prescription drug, like if we're testing a drug, and we are giving these kids that have ADHD this drug, and then we are having them report, if we give them the drug and we see that we are seeing reduced levels of something that we're looking for, that could imply that the drug is causing that. You would also need to make sure you kind of like rule out other things that may be happening for that. Yes?
Yeah, I remember a story about that.
Well,
I heard there was like a group of like 30 kids that they picked out everybody that acted differently, and they got them on ADHD medicine. They were like zombies.
I do think that those medications are probably overprescribed.
Yeah, they did try to get me. They told me to be on it.
And they're,
Before my parents threw it away.
I do think that they can be overprescribed because sometimes people find that the answer when it may not be, but certainly there can be cases where it might be necessary or be helpful. But yes, now as far as the school goes, the school cannot make anybody take any medicines. We can't even recommend it. We can say these are the behaviors that we are seeing. You need to consult. Well, a teacher can say these are the behaviors that we are seeing and we think you should be evaluated. But we are not doctors. So we can suggest that you should be evaluated, but only doctors can prescribe that or diagnose that. So doctors may go a lot on what teachers say sometimes, but doctors are supposed to diagnose that. And I do think sometimes it does go a little. And parents if parents want you to be on it, then that has, versus don't want you to be on it, that has a big effect as well. Well, I could go read the list of symptoms for something right now and go say that I have all those symptoms and probably, yeah. I mean, the better doctor you go to, the less you would be able to do that, but certainly. Okay. And that could, I just threw that one out there because it's a fairly common prescription that we see, but it could be anything. You should look at correlations to see if there is a cause there. It definitely should be evaluated. All right. Okay. So, correlation, we can describe it using the correlation coefficient, which we have done before. Sometimes we just describe it with words. So, I'm going to label these. I'm going to call this one A, B, C, D, E, and F to make it easier for us to talk about these. Which ones of these would have a positive correlation? Okay, A and B would be positive. I agree with those statements. Which ones would have a negative correlation? The C, D, E, these are negative. What would you say about F?
No correlation.
Okay, F, okay. F, I would say that F would be a no correlation.
No.
Actually, it may have been because I put boxes over these because I couldn't get rid of them. Then you can also talk about the strength of the correlation. So which one on here do you think is probably the strongest correlation? Okay, I would say A is strong. C is also strong.
So is E.
Okay, is E as strong as A or C?
No.
I don't think so. I would call this maybe moderate. Medium. Okay, I would call it maybe a moderate. It looks a lot like a line, but it's definitely not as tight as the other. Certainly there's some level of just judgment here on what you're deciding to call these. All right, what would you say about B or D?
Loose.
I would call those weak, at least compared to what we're looking at up here.
Not the word.
Okay. All right, questions? All right. All right, so let's talk about residual plots and correlation. Okay? So looking at these two right here, which one of these would show a stronger linear correlation?
I disagree.
This one. Okay, now let me tell you why. Okay? A stronger correlation. Now we don't have an y-axis here that would affect this. But if we have a pretty strong correlation, we should see dots both above and below. They should sort of be scattered. They shouldn't make a pattern. And the closer they are to the x-axis, the better, right? So you can see over here, we've got both above and below. They're kind of even here. If you see something like this, where you see a pattern in your residuals, so we can see that they're all negative over here, they're all positive here, and then they go negative again. Or, well, yeah, because there's their 0. So if we see a pattern, so a pattern indicates that the data may not be linear. So what may be happening here is that maybe you've got, so like for example, if I had exponential sort of points and I tried to make a line through them, notice how everything over here would be above the graph, then it'd go below, then it'd go above again. So if you're seeing a pattern, it may indicate that you are not actually looking at linear data. So if you see that something like this happens, it might be exponential or quadratic or something else may fit it better. But for linear, you should see them sort of scattered all over the place, above and below. And again, now if there was like a third option and we had a residual plot and they were scattered but they were all way closer to the x-axis, that would be even better than this one here. But if you see a pattern in your residual plot, then it's probably not going to be very linear. Does that make sense? All right, so we have an assignment here.
What is that? Transformers?
You can take it. The Russians created World War I. Period.
Yeah.
Government conspiracy.
The UK?
My real name.
Yes. I don't know, they're just gone. There's no notes in the computer about